Okay. So, we have polarity dependent rate constants, that is for sure, and there is some effect of hydrogen bonding. So, the second piece of experiment that they did, earlier one, remember what it was? It was mixtures, isoviscous mixtures at room temperature. Second experiment is in isoviscous liquids at different temperatures. It is important to understand what we are talking about here. As you change the temperature, I think it is very well understood that viscosity of a liquid is going to change. Does it increase or decrease usually when I increase temperature? And what about a gas? Why? For a gas, viscosity increases with increase in temperature, that is right. For a liquid, it decreases. The molecule collision, that is liquid, you understand nicely, right? What about gases? So, you think of laminar flow, there is exchange between different lamellae, that is why. Okay, but right now we are talking about liquids anyway. So, what it did was, they painstakingly determined the viscosities of neat liquids at different temperature. And then of course, you have to eliminate the, you cannot compare an alcohol with a nonpolar solvent. Okay. And then at different temperatures, they took different solvents, keeping in mind that viscosity has to be same for all these points. So, solvent A at 25 degrees centigrade, solvent B at 35 degrees centigrade, solvent C at 45 degrees centigrade, so on and so forth. The common factor is that at 25 degrees centigrade, whatever viscosity solvent A has is the viscosity of solvent C at 45 degrees centigrade. Okay. Isoviscous neat liquids in different temperatures. And then they observed the surprising result that the rate of TICT increases at lower temperature. That is not a very usual phenomenon, right. It is not as if it is unknown. Again, if you go back to Atkins physical chemistry book or any standard physical chemistry book, you will see that if there is a pre-equilibrium, then you are going to have, when certain conditions are met, you can have a decrease in the rate constant with increase in temperature. Okay. But here the explanation is this. This here, let us say, is your energy surface for the locally excited state. This is the energy surface for the charge transfer state. So, what they said is that the charge transfer state is going to be stabilized further if polarity is more, yeah, and polarity is more at low temperature. Yes. So, what will happen? You can see there are two surfaces here for CT, the upper one and the lower one. If suppose there are two temperatures, which one will correspond to the lower temperature, which one will correspond to the higher temperature? Yeah, lower one corresponds to higher temperature or lower temperature? Lower temperature actually, because at lower temperature your polarity is more or less. Oh, I did not even discuss that, we only talked about viscosity, sorry. At lower temperature actually polarity is more, because at higher temperature what would happen is your solvent dipoles would rotate and all, that would cause a decrease in dielectric constant. So, at lower temperatures due to greater polarity, this would be stabilized. You might think that that should have no effect on the activation energy anyway, because you are stabilizing the product. What does that have to do with your activation energy? Actually something is there. What is there? Look at this diagram carefully. If it comes down, what is the activated complex? It is a point at which the two potential energy surfaces for LE and CT cut, right. So, if the LE surface is where it is and the CT surface is lowered, then what will happen is that the two surfaces will intersect at a lower energy point. Okay. That is what will lead to a decrease in activation energy at low temperature. Okay. So, Arrhenius equation is not violated. Arrhenius equation gives you the expectation that if you increase the temperature, rate should increase, but that is true only for constant activation energy scenario. Here the activation energy itself becomes smaller, because it is not only temperature that you are changing, and this is instructive because you have to remember when you try to understand the photophysics of any molecule, that you change some parameter, it is not the only thing that is changing, it can have a domino effect. So, you have to be very careful about what you are actually looking at. You think you are only changing temperature, but are you affecting viscosity, are you affecting polarity, are you affecting molecular aggregation or deaggregation? One needs to think of that. So, now to conclude this story, they observe this empirical expression, but EA equal to EA 0 minus A into ET30 minus 30. Now, it is accidental degeneracy. The second 30 has nothing to do with the first 30. The first 30 is a roll number, second 30 is a number that arises out of experiment. It is fortuitous that they are the same, or maybe they made sure that maybe they change the roll number so that this becomes roll number 30, so that both are 30, but these two 30s are actually not related. Okay. So, from here what they established is that the activation energy of alcohols is greater than the activation energy of nitriles. And more interestingly, the difference between the activation energies of alcohols and nitriles is 6 kilocalorie per mole. Does this number ring a bell? 6 kilocalorie per mole? What is it? The 6 kilocalorie per mole. It is the energy of a hydrogen bond. So, this difference in activation energies of alcohols and nitriles is due to hydrogen bond. So, hydrogen bond also has a role to play, and this one letter contains so much of information and is so instructive. It is imperative that we all read this paper and understand it. There is more to it than what I have presented, of course. It is important that we understand everything. Please read this paper. Great. To conclude this story, even though we have overshot the time a little bit, we will finish this and then maybe today we will stop. So, TICT in DMABN is the champion molecule of TICT. This what champion is used very commonly, especially now in the heydays of material science. People make devices, they make 200 devices, and the one that is best performing is called the champion device. So, there is no harm in learning from there and calling DMABN the champion molecule of TICT, but then that is not the only prominent TICT molecule, there are plenty. Two other, these are also champion molecules, classes of molecules are Nile red and TNS or ANS for that matter, T for toluidine, A for aniline. So, these are all TICT molecules, and Nile red and TNS, ANS, the claim to fame of these molecules is that they are used extensively by people who try to understand proteins using fluorescence. These are very well established protein stains, extrinsic protein stains. And the idea is, and you can see this is the data that we recorded, I think when I was a PhD student or something. I think this is ANS or TNS, I forgot, maybe ANS. So, this is the spectrum in water, but multiplied by 66. So, if I do not multiply by 66, it will be a baseline, right. And you see when we put it in micelle, there is a huge increase and there is a blue shift. Why? This is the TICT emission that you see in water, and since TICT state is energetically closer to the ground state, non-radiative deactivation of that state is much more, that is called the energy gap law. If the energy gap between two states is small, then the rate constant of non-radiative deactivation between these two states is an exponential function of that energy gap, okay, widely used in things like metal ion complexes. And when it is put in micelle, then the micropolarity is much less. That is why the locally excited state is selectively populated, that is much more emissive, higher energy and more emissive. Okay. So, these are two examples, and there are many applications that are worked out. This is not such a great example, I do not know why you have put this one. There are if you read the work of say Professor P.K. Bharadwaj of IIT Kanpur, they have made numerous devices and all, not devices, sensors and all, and their strategy is always you have an ICT molecule. Initially ICT is there, since ICT is there, fluorescence is quenched, then you bring in a metal ion or whatever you want to sense, and that engages the lone pair. So, ICT is stopped and fluorescence shoots up. That is what makes turn on sensors. So, you can read this, it is not so bad also. You can read this paper for description of this sensor that they made of different things. Okay. Now, we go back once again to 1993 and show you some data where people have tried to do structural modification of DMABN. I am going very fast on this part because I want you to actually read these papers. This is homework. I do not expect you to understand everything I am saying right now, it is just an introduction. But the crux of the matter is people tried to make DMABN derivatives of several different structures, one in which this coplanarity will be maintained, one in which coplanarity is forcibly destroyed. And in all these studies, what they inferred was that the twist takes place. If you do not allow the molecule to twist, you do not see that TICT band. Okay. If you force it to be at 90 degrees, you only see the TICT band. But then there are problems also, because if you make the linkers a little too long, then all results go awry. Now, before leaving this subject, I should at least show you some real ultrafast dynamics data. So, let me do that, and this is where we will show the data we promised. Okay. In this 2009 paper, what you see is, this is, what data is this? Can somebody guess? Upconversion, right? But upconversion with the difference, as we will see. So, this is the dynamics in the blue end of the spectrum. Okay. Mon is not Monday, I think it means monitored at 350 nanometer emission wavelength. You see there is a decay, and the decay constant is 3.07 picosecond. Ignore that 2 in bracket. And when this trace is recorded in the red end of the spectrum, you get a rise associated with 3.07 picosecond. So, this tells that 3.07 picosecond is the time associated with the charge transfer, locally excited state to charge transfer state transformation. Okay. And this is a kind of a nice way of putting it, and it gets nicer when I show you the time resolved emission spectrum. Here they are. Does something strike you here? These are not fitting curves. These are actual fluorescence spectrum recorded at different time delays. The entire fluorescence spectrum is recorded together. Okay. And now again I want to give another homework. The homework is this: we had actually gone to our lab and looked at the Fox setup and saw how it worked. Femtosecond optical gating depends on generating a sum frequency, and as we have discussed earlier, for different wavelengths, well, the gate light is the same wavelength, for different emission wavelengths, sum frequency generation would take place at different tilts of the nonlinear crystal. And over the last 10-12 modules, we have learnt why tilt is important also. Okay. So, what common sense would tell us is that the tilt at which we get some frequency for a particular emission wavelength lambda 1 should not be appropriate to generate some frequency using another wavelength lambda 2. Is that right? This is a tilt, it is optimum for lambda 1, which means some frequency for lambda 2 is not going to take place. Then how do I generate the entire spectrum? The entire spectrum is recorded at one go, like our transient absorption spectrum. How has that been done? It can be done in two ways. First, the hard way or the more time consuming way. Use a stepper motor on the sum frequency generation crystal itself, right, and keep tilting. So, this tilt may be the angle for say emission wavelength of what is given here 350 nanometer. this may be the actual the appropriate tilt for 355 nanometer. So, keep on tilting the crystal, okay. And as you know, we use uniaxial crystals. So, tilt is the only parameter and keep on recording data, okay. Hence construct the spectrum, but if you want to do that, do not forget how it is done. Fix the tilt, then run the scan. So, essentially you generate the decay at that wavelength, then change the tilt again, record another scan, that is the decay. So, in this method, if you want to do it in this method, you actually generate the decays first and from there you construct the time resolved emission spectra, okay. The other way of doing it, and that is something that we have not really discussed, is to use a very thin crystal in which that tilt is not important. You can get some frequency for all the wavelengths. What I want you to do is, I want you to read this paper and tell me next day which method has been used in this paper. Is it a variable tilt or is it a crystal at a particular angle, but thin enough so that you can get all the wavelengths together, okay. And in the second case, how does it work? Next day we will start with this question, right. So, we have talked about TICT, we have shown plenty of evidences for it and we have discussed the ultrafast dynamics of it, we have discussed your applications of it as well. The only thing that remains to be discussed now is the opposition to TICT. Because remember, I started off saying that this is perhaps the most controversial excited state process ever discussed. Maybe not. If we get time, we will talk about the proton transfer debate between Tahara and Zuel, 7-aza-indole dimers. And I say Tahara and Zuel because Tahara turned out to be right, Zuel turned out to be wrong in that debate that lasted a decade. But why do I say it is controversial, TICT? That is because there has been a school of thought, a minority school of thought, which has said from day one very vigorously that this twist is not important. And that school has been led by Professor Zacharias, K. Zacharias. And in heydays of TICT, whenever I read their papers, I felt that this guy is making too much of sound for no reason. But then in 2004 or so, there was this paper from Zacharias group, and this is a pump probe experiment, but it is a UV pump X-ray probe experiment, and it is easier said than done. It is not so easy to do an X-ray probe experiment, it is quite involved. If you read this paper, you will see that there are things that we need to do beyond what we have discussed. What is a good thing about having an X-ray probe? Who are the people who love to do X-rays? In chemistry department, of course, inorganic chemists. Why? Because they have such strange complicated complexes, right. So, X-ray crystallography is what tells them what the structure is, and it is not only inorganic chemists, even protein crystallographers love to do it, okay. So, X-rays give you the structure. So, what this paper did is that it showed, now you are doing pump probe and probe is X-ray. So, it basically gives you the structure of the molecule in the excited state, and once you know the structure of the molecule in the excited state, the question of whether it is tilted or whether it is straight in the excited state is laid to rest forever, because you can see the structure. Analysis is non-trivial, and also the molecule they used is a little different. But what they saw there is, they said that there is a greater amount of planarization in the excited state compared to the ground state. It is a completely opposite view. TICT says the ground state is planar, coplanar, excited state is twisted. What these guys say is that the ground state is not planar, it is something like this, excited state is more like this. planarization. So, all this discussion falls apart. What does not fall apart is the fact that the charge transfer state is highly polar and there is a viscosity dependence. Okay. After this paper, not many papers have been written on the TICT, but it is not as if the debate is over. I leave it to you to read this paper by Catalan. I will only highlight the acknowledgement. What he wrote there is that I am indebted to Professor Zacharias, whose apt criticism of my recent paper on the photophysics of DMA-BN encouraged me to devote the past 3 months to carefully revisiting existing evidence for this compound. So, even though the intensity of debate has gone down, frequency of papers has gone down, it does not look like anybody is giving up. So, over the last 30-35 years maybe, there is intense discussion about what exactly goes on in so called TICT molecules. One thing is for sure that charge. So, ICT part of TICT there is no problem, whether it is T or whether it is P or whether it is nothing. That is where the debate lies, and the useful byproduct, if you want to call it that, of this debate is that we have first of all got a lot of useful information on these kind of molecules, based on which some applications have been designed. To me, what is more important is that in the attempt to understand this, the intricacies of this process, we have actually learned a lot about how to perform experiments and how to interpret data if you are going to attempt to answer a question like this. To me, that is the biggest outcome of this entire debate. We stop here today. Next day, we talk about something that is another fundamental, that is about another fundamental question. How much time does it take for a solvent shell to form around a polar solute, or in other words, solvation dynamics.